So this is supposed to be a quick review of the solutions. Because it's a recording, you can pause and rewind at any point, but I'm just going to quickly go through the solutions together. So if we have an input to a multiplication operator for our vector space, remember the addition operator is v box plus v, and the multiplication operator is f dot box v. So it's a scalar and a vector, but it's the scalar then a vector. So scalar then vector. Okay. Now the next question is asking if this set is linearly dependent or linearly independent. And that's a way of saying, can I make a vector out of the other two vectors, or can I add them to create 0? Well, if we look at 1, 1, 1, if we subtract off or add -1 times 1 times the first vector plus -1 times 1, 1, 0, and -1 times 0, 1, 1, or 0, 0, 1, we get the 0 vector, which means we have a linear combination. So we have vectors times scalars that give us 0, where our scalars are not all 0. So we have 1, in this case, every one of them is not 0. So we are linearly dependent. Now here we want to set up a system of equations to determine if x is in this span. So here what we have is we have 0x squared plus x plus 0 times x to the 0 is equal to, and now our first variable, we're going to be asking, is it equal to a times 0x squared plus 1x plus 1 times x to the 0 plus bx squared plus 0x plus 1x to the 0 plus c x squared plus x plus 1. And if we expand, we're getting 0x squared plus 1x plus 0x is equal to b plus c x squared plus b plus a plus b, or a plus c x plus b plus c, or a plus b x to the 0. And now, collecting like terms, we get a system of equations. So our coefficients for our polynomials, our coefficients for our coefficients for our x squared terms, our coefficients for the x to the 1 terms, and our coefficients for our x to the 0 terms. So here we have b plus c equals 0, a plus b equals 1, and a plus c equals 1, and a plus b equals 0. And there's our system of equations. Next, we're going to be computing a division of complex numbers. So remember that the division over 2i divided by 4 minus 5i, we multiply by the complex conjugate of the denominator. So we're multiplying by 4 plus 5i over 4 plus 5i. And now if we expand the top, we're going to get 12 plus 8i plus 15i minus 10 over 16 plus 25, which equals 2 plus 23i over 41, which is equal to, we separate it, 2 over 41 plus 23 over 41. Now we go to 5. Now, with 5, let S be a subset of a vector space, and S contains the 0 vector. Can S be linearly independent? Well, 9 times 0 equals the 0 vector. 9 times the 0 vector equals the 0 vector. This is a linear combination in S. It's multiplying elements of S to create a linear combination. Even though it's not adding to any other vectors, it's still scalar times a vector. And our scalar is non-zero. So because our scalar is non-zero, we satisfy there exists the linear combination with a non-zero scalar such that the linear combination equals the 0 vector. So no, we cannot be linearly independent. We are linearly dependent. Now we have provided an example of a set S in R2 such that S is not a subspace. And we could give any example where we have a set of vectors not including the 0 vector, but not the span of that vector. So the set of vectors 1, 0 is a classic example for a subset that is not a subspace. Okay. Now we want to know when a system of equations is inconsistent. And this is when no solution exists. Okay. Now, A8, we consider the following vectors. And we're asking, is 1, 0 a redundant vector? And if we look in this set, 1, 0, 0, 1, and 0, 2. Well, 0, 1, and 0, 2, any combination of 0, 1, and 0, 2 will only have entries in the second entry that are non-zero. The first entries will always be 0. If I look at A, 0, 1 plus B, 0, 2, this equals 0, A plus 2B. So it'll always be 0 in the first and then numbers in the second. But this entry, this vector, has the 1 in the first entry, and it cannot be made using these other vectors, which means if we remove it, we won't be able to generate entries in the first, so our span will be different. So no, it is not a redundant vector. Now, I want to list 2 axioms of a vector space. So here I'm listing 2 axioms of a vector space, and the classic ones are the addition operator is commutative and associative. There's our 2 axioms of our vector space. Now, the last thing we're going to do is we're going to construct the system of equations to determine this vectors in the span. So that's asking, is the vector 1, 1, 2 equal to A, 1, 2, 3 plus B, 1, 0, 0 plus C, 0, 2, 3, or is 1, 1, 2 equal to A plus B, 2A plus 2C, 3A plus 3C. Or if I make a system of equations, 1, 1, 0, 1. Oh, that's not a system of equations. I was going to the augmented matrix. Let me make a system of equations, not an augmented matrix. So the system of equations is A plus B equals 1, 2A plus 2C equals 2, 3A plus 3C equals 2. And here, one thing to note is you ask yourself, could this be consistent? Or could it be, and if we look at these 2 rows, well, if I subtract 2/3, if I divide this second row by 2, and then I take the third row and subtract 3 times that resulting row, we're going to get that 0 plus 0 equals -1. And that's going to be inconsistent. So this actually doesn't have a solution. So we're not in the span. So when you solve this system of equations, if you were to determine if it was in the span, then we would go through and we'd find out that it's not in the span. It's linearly independent of those vectors. But remember, this question is not asking us to determine, it's asking us to construct the system of equations to determine. So it's saying just get to this point. This system of equations is the equation that we would use to determine if it's in the span. It's not asking us, we're not determining if it's in the span. We're just setting up the system of equations that can be used to determine if we're in the span.